Now, so these are the rules and these are the steps that you should remember. Okay, so either start with the longest, or if the one that you need to find is a short energy process, for example, NW change of formation. Okay, so it's only pointing from elements to a product, for example. You can start with a longer chain, which basically connects more species, right? If the one that you want to find is already long enough, okay, it's a complicated reaction that you cannot find in lab, then yes, that will be your main equation, okay? Now, so with that, right, you choose either the longest or the main equation that's long enough, okay, that connects all of the species that you need. Now, it must be with state symbols, remember, and balance coefficient. Okay, balanced stoichiometric coefficient clearly indicated. Now, please make sure that your equation is really, really balanced right from the start. If the starting, okay, horizontal equation that you are writing, okay, is not balanced, the whole cycle will be basically problematic. Okay, so make sure you spend time to balance this properly. Okay, now, so you need to know what you have. So you have data booklet. Now, data booklet have two kinds of energies that you can use, meaning the question will not give you. Okay, the question will not give you. So for example, ionization energy. So ionization energy allows you to convert gaseous atom to cations. Okay, be it a single, double, triple. So depending on how much of the how highly charged your cation must be. So you basically perform either first, second, or third, i.e. depending on how many charges you need the cation to be. Okay. Secondly, your data booklet also have your bond energies. Now, what are bond energies for? Remember the first lesson, your bond energies are to convert gaseous molecules, whether or not they are compound or elements, to atoms. N2H2O2 Cl2 F2. Okay, these 5 gaseous elements will not be given for atomization, for creating atoms of these molecules, from these molecules. And also, if you need to break any covalent bonds from your molecules, they might not be given, and you might need to tap on to bond energies whenever you need to create gaseous atom. Okay, so make sure you remember that. Now, you have to memorize your definition well, because if you don't remember definition well, you have no idea what kind of equation you need to put into your cycles. You have to do some matching to the from the main equation to the equations that you have and is given by the question, right? Or in your data booklet. As you connect as many intermediates as you can to complete the cycle. Now, please remember the cycle, okay, it's a cycle, it's a closed loop, must be closed loop cycle. Meaning you must point always from the start to the end. It must be closed loop, right? Now, these are the rules that you need to remember, okay? So which we learn right from the start actually. When the equation is reversed, for example, I give you a reference value already. So it's hydrogen plus iodine gaseous form to give you hydrogen iodide gaseous form. If you ever need to reverse the process, okay, then the value will be reversed, okay, with the same magnitude. Now, what second point is also we learned before, when stoichiometric coefficient is multiplied, the delta H is multiplied accordingly, okay, because this is per mole of this equation. So this has twice as much HI form as compared to your reference value. So it must be multiplied by 2. Whenever you have a species that you need, but it's not found in the main equation, you have to add it on, okay? And when you add it on, you make sure you add it on to both sides of the main equation so that it is cancelled off, and basically the equation will still be the same as what your reference will be, okay? So adding on species to both sides of the equation, the delta H remains unchanged. So this is a very useful trick to complete our cycle. Right? Now, substance should move together as a collective group. So later on, I'll show you what is this. Now, so how should we calculate? So imagine this is the delta H that we are calculating. And therefore, we are taking the root of from here to here to here. This is our start. This is our end. So always write start and end in your mind, okay? Or you can write it down, right? So basically what you need to do is to have the arrows pointing from the start to the end, okay? Now, so if the arrows of the processes are along the your train route will be, how your track will be from the start to the end, then is summation. So for example, delta H1 is pointing the same direction as how my cycle will start and end. So it is summation. So it's delta H1 summing up. Okay, you see there's no negative sign in front of it. Then the next one is for delta H2, you can see that the arrow is pointing a reverse direction as what I will wish to complete my energy cycle. So therefore, it will be a subtraction. So I add in a negative sign for delta H2. And delta H3 is along the cycle arrow. So therefore, it will be a summation. Okay, I hope this is clear enough. Now, note that each of the delta H's can be positive or negative on its own. So these signs, okay, these positive or negative signs are really just whether you are against or along the pathway where your energy cycle will go from the start to the end, right? So that's how we will calculate. Now, so let's look at our questions and let's do some cycle drawing. Now, for example, if we look at skill 5, question number 32, we will start with the longest cycle, longest equation, okay? Now, for these two processes, you can see that this is chromium oxygen to chromium oxide. This is like a combustion. And then carbon combusts to give you your, and with oxygen to give you your carbon monoxide. This is not combustion, this is formation of carbon monoxide. Now, can you see that this is the equation that connects all of the species, be it carbon, chromium oxide, and chromium and carbon monoxide, okay? So this should be the main equation that should be horizontal. The other equation should be like pointing in other directions, okay? But you should be writing equation, but in other form, okay, right? Whether is it pointing down or pointing across, okay? So let's start. Now, so we start with whatever we have on the cycle. So let eyeball whatever you have. For example, I will look at carbon. Okay, so since I have carbon here, one more rule before we start. All these value you can change. You can manipulate it. Okay, you can manipulate it. You can multiply that by 3 times. You can divide by 3 times. You can manipulate. But this one, don't change. Don't touch it. Okay, don't even touch the don't even touch the equation that they want you to find, right? Because this is impermo of this equation. So don't ever touch this. So you can manipulate. For example, okay, I find a common species. So this is my carbon and it's 3 times, right? But I don't have 3 here, but what I can do is multiply by 3. So I might multiply by 3, multiply by 3, multiply by 3, and multiply by 3. Okay, so what am I going to do is I have to convert carbon to 3 carbon monoxide gaseous. So make sure state symbols are all copied correctly. Okay, the starting state symbols are correct. Now you do notice that I do not have oxygen in my balance, in my equation over this side. So I don't have oxygen here. So what am I going to do? I have to add in oxygen. So I have to add in 3/2 moles of oxygen. Now, because oxygen is not in this main equation that I wish to calculate the value, I have to add also, let me erase this part, so make sure this one no change. I have to add also 3/2 O2 gas to the left and right. Okay, so therefore, I get to use this 3 carbon plus 3/2 oxygen to form my 3 carbon monoxide. Are we okay? So this will be, write down the value immediately, 3 times -110. Okay, and we point from start to the end. So I'm following this arrow pointing. Okay, now same thing, this chromate, right? This chromate, now this process, this energy will not include the reaction of chromate. So what we do, we copy down anything we don't use, right? We copy down exactly the same species. So that why this equation, basically this is cancelled, right? So it just involves carbon and oxygen combustion or reacting to give you your carbon monoxide. You understand? So it's very important to move your chromate, okay, down. So this is what we say, everything must move collectively. Okay, so anything that you don't want to use it for this reaction, you copy it down. Right, now next, the other reaction, the other equation that we have is 2 chromium plus 3/2 oxygen to give you your chromium oxide. Now, when one side is balanced, right, you see that it is very easy. You just need to point. Can you see you have 2 chromium here and 3/2 oxygen gas? So what you need to do is just to point, and basically this process, it's -1130 because it's exactly the same. 2 chromium plus 3/2 oxygen. 2 chromium, 3/2 oxygen. And what do you have? Carbon monoxide, and carbon monoxide will cancel here. So this energy process does not involve the change of carbon monoxide. So it still keep the same energy value. And there we go. We complete our cycle. Everything is in a closed loop already. Now we can calculate. Okay, now it's about the calculation. So the delta H of the reaction here. So what do we have? We have start. So let me write a start. Imaginary, your eyeball need to have start and end. Okay, so follow my green arrows. The green arrows is the energy cycle arrow. So I'm pointing along here and pointing against here. So therefore, because this is along, so we will have to add to 3 times of -110. Okay, add. And then this is against, so this is against this value. So therefore, we have to minus, okay, that delta H of that reaction. -1130. Press your calculator carefully. You should get your answer to be plus 800 kilojoules per mole. Okay, you need to draw an energy cycle, correct? They never force you. You must draw the energy cycle in energy level diagram. So don't bother to do that. Okay, don't need to do that. Just draw a cycle. A cycle is usually easier to draw than an energy level diagram, because energy level diagram you need to worry about many things. Now, so first trick. Okay, first trick. Number 1, always read what you are supposed to find. Okay, number 1. So let's read what we are supposed to find. So they will give you many values. Okay, use these, okay, together with the blah 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 to determine standard heat of formation. So basically what you want to find is just formation of 1 mole of your C2H2 gas. Okay, so if you look at the equation, right, the formation equation is 2 carbon solid, okay, plus 1 mole of hydrogen gas to give me 1 unit of C2H2 gas. So the equation, right, is too short, right, too short to represent as the overall horizontal equation. Never start with a short equation, okay? You will end up yourself with bigger trouble later on. So always find something that is longer. Okay, and it basically encapsulates, it involves what you need to find also. So for example, right, you check, I need to find something with a C2H2, which is longer equation. So out of all the equations, this is the best. Can you see you have a C2H2 there, and it's 1 unit, just nice what you need to find. Okay, so we are going to use this. So let's copy this down. Zinc, so zinc carbide plus 2 water liquid, okay, gives you zinc hydroxide plus C2H2 gas. Okay, so important, whatever you choose in the overall starting equation, number 1, choose as long as possible. Number 2, it must involve what you want to find. Okay, try your best to involve what you want to find. You will start with that. That is the easiest way, right? Now, so let's start with matching, right? So first, since we are using this equation, so let's put in the energy value -126. Okay, so we are done with this. So I'll put a tick so that we will not look at the equation again. Now, next one. So let's try to link the things up. So we have, you can start anywhere. You can start with water. Okay, you can start with water. You can start with zinc carbide. Both sides. Okay, you can even start with here also. Okay, both sides have equal numbers, so it doesn't really matter where you start. So let's start with here. Okay, the left hand side. So let's look at zinc carbide. So zinc carbide appears here. Okay, but as a product, as a product. So therefore, right, what I will do, I will copy, okay, the equation exactly, since it's 1:1. So the arrow, right, you keep it, you don't switch it around. Keep the arrow and point towards the zinc carbide as a product. Okay, now you realize that now zinc carbide is there, right? It's here. However, it's missing this thing, this species, your carbon monoxide. So please apply the trick. You add your carbon monoxide in. You add your carbon monoxide in, but not only to the left hand side, you must also add to the right hand side. Okay, so that the horizontal equation still is represented by -126 kilojoules per mole. Right? Now, so therefore, right, if you zoom into the equation, we already have the products. Now we just need to put in the reactant. So zinc oxide solid plus 3 carbon solid. Okay, and this value is represented by plus 462. This equation is represented already. Now remember, anything that's extra that it doesn't belong to that part of the reaction, copy it down. I never use water at all, right? So I just copy it down, right? So that the equation at every one part is always balanced. Now, so let's get the next part. Now, so with the zinc oxide, okay, I'm going to use this already, right? Because there is the zinc oxide there. There's 1 unit of water there. So you see I have zinc oxide at 1 unit of water, right? So after using it, what will I convert? I'll convert zinc oxide to zinc hydroxide solid. So I'm going to copy everything down. Now, anything that you don't use, the 3 carbons and that 1 unit of water that you don't use, copy it down as well. So I'm going to copy the things down in black. So 3 carbon solid plus 1 liquid water. These are the things that you never use, right? So the equation here, right, where you have zinc oxide reacting with 1 unit of water to become zinc hydroxide, the energy value is -65. You can see that we are nearer. You see, can you see zinc hydroxide is here? We already formed zinc hydroxide. Okay, what we need to do is to convert the carbon to carbon monoxide, which is shown here, or to convert the liquid water to your hydrogen and oxygen gas. So let's do that. So let's do liquid water first. So this is 1 unit of liquid water, but there is 2, right? Remember, this one, everything here you can manipulate. Here you don't touch, you keep to 1 unit of water. Now I'm going to follow the arrow. So this 1 unit of water is going to point to hydrogen gas and oxygen gas. But because it's 1 unit, right, this is shown you 2 units. So I need to halve positive 572 and make sure that my products are all halved as well. Okay, so that means this whole equation, you multiply by half. Now, everything that I never use, I'm going to copy down in black again. So zinc hydroxide, never use. So I'm going to use, copy down zinc hydroxide, solid. The 3 carbons never touched, so copy down 3 carbons. Oh, okay, and plus everything together. Now, so let's continue. I can convert because we need 1 carbon monoxide here, right? So I can convert using 1 of the carbon to carbon monoxide first. Or I can also do formation as well. Formation of what you need to find. So either or, okay? So let's choose to do the carbon monoxide first. Okay, I'm going to convert this to carbon monoxide. So carbon monoxide, this value is -221, but please remember, because this is for 2 moles of carbon monoxide, you got to times half. Zinc hydroxide, I never use. Out of 3 carbons, okay, sorry, my C is missing. Out of 3 carbons, I only use 1. So basically, I need to have 2 more carbons here. Okay, and the hydrogen gas, I never use, so I copy it down as well. Right? Now, therefore, final equation, which is what you want to find, your formation. So basically, can you see carbon monoxide is carbon monoxide here, zinc hydroxide is zinc hydroxide. They do not take part in the reaction when we are pointing from here to here. It is basically representing enthalpy change of formation of C2H2 gas. Okay? So we have closed our cycle. And now let's apply mathematical formula on it. So apply the Hess law. What we want to calculate is start here. You have to, okay, start from here. That means, right, going from here all the way, this direction, and end here. So therefore, your enthalpy change of formation of C2H2 gas is equals to, let's start from the bottom. So it is a reverse of sign. So minus half times -221. The next one is also minus, because it's reverse, half times positive 527. And this one is also reverse, right? This is also reverse. So minus -65. And this is along, plus 462. And this is along, right, in the same direction. So plus negative 126. And therefore, you should get positive 225.5 kilojoules per mole. Okay, now let's try again another energy cycle. Okay, magnetite can be produced by this reaction. So this is the reaction. It looks like a lot of species, so we might be able to use this as the overall. Then they say heating leads to the formation and oxygen gas. So they give you another equation here. Okay, using the thermodynamic data provided, so they provide this, calculate enthalpy change for the reaction. So they want you to calculate this. So this is what you want to calculate. Take note of the mole ratio, okay? Because whatever you want to calculate must have 3 moles of Fe2O3 to 2 Fe3O4 solid plus a half oxygen gas. This is what you want to calculate, so make sure the mole ratio is represented, well represented in your equation that you want to start with. Now, so the next few data that they provide you with is formation, combustion, vaporization, all very small equation. You shouldn't ever start with this. Now, so what you want to start with is a very long one, which includes what you want to find. So for example, your iron Fe3O4 is there. So I think this is the best. So let's choose this. Another thing is check the mole ratio. Now the mole ratio here is only 1, right? But what you want to find is for 2. So make sure you manipulate it and change everything here to 2 times. Okay, you times 2 straight away, right? Because what you want to find has 2 Fe3O4 solid. So let's multiply by 2. So you have 6 iron solid plus 8 H2O gas to give you 2 Fe3O4 solid plus 4 hydrogen gas. Okay, now so don't overcomplicate. Don't need to think, oh, what should I do first, second? Basically, right, once you write in the equation, you find the links. Okay, then you consider the links. So what is the decision you need to make first is find the most appropriate equation to start with, check the mole ratio, make sure you get the exact mole ratio that you need. Okay, then you start. So this is negative 2 times negative 515.1. Right, so let's start. So I start with formation of Fe2O3. I don't have this yet, so I cannot do anything here. Right, let's combust our hydrogen. Okay, we burn our hydrogen. So burning our hydrogen, you can start whether or not left or right, doesn't matter. Vaporization of water is to convert liquid to gas. Same number of species on both sides. So let's just choose to start on one side. So let's say, okay, I want to vaporize my liquid water. Okay, that's the only one that connects to gas first. So 8 moles of water, liquid, to convert to 8 moles of gas. So it's 8 times 40.7. Whatever that I don't use, I copy it down first. So iron, solid. Then after that, they have combustion. So once it's liquid water, I can connect the combustion already because combustion of hydrogen connects to liquid water. Combustion means water is the product. So I'm just pointing to water also. So I burn 8 units of hydrogen gas, right? Plus 4 units of O2 gas. Because I'm forming 8 units of water, so it's 8 times negative 285.8. We add in the iron as well. So iron till now haven't take part in the reaction, so just copy it down. Now you see your oxygen gas already, right? And you see your iron, you can start to form. So to form Fe2O3, right? Since there are 6 units, I need to form 3 units of Fe2O3. So the total number of oxygen you use is 9. You see, I need to add another half to make sure it's 9. So once I add this, right, I need to add backwards also. So half, okay? And then half, right? And then half here. So I need to add to every part. The oxygen is settled. The iron is settled. Your hydrogen, right? Your hydrogen, we should copy it down because we never use it here because it's formation. So formation of 3 units of Fe2O3 plus 8 units of hydrogen gas. Now I realize, hey, why my hydrogen cannot connect? So that's when, as and when you do the cycle, you need to check. Cannot connect, meaning some parts must be catalyst mistake. Okay? Now, so we are really at the end because we don't have any values that we can apply already. So check whether you can connect. So if you see carefully, you have 3 of the iron 2O3 forming 2 of the Fe3O4. So it is here already. Okay, it is here already. The hydrogen gas will cancel itself and you will plus another half unit of oxygen gas. So therefore, pointing up, this is just your delta H of the reaction. So let's do the mathematical calculation. Start and end. So therefore, I'm going to start from here. So this is in this direction. This direction. The delta H of the reaction is equals to, so reverse, so minus 3 times negative 824.2 along, right, plus 8 times negative 285.8 along, so plus 8 times positive 40.7, and this is also along, so plus 2 times negative 151.1. All right, so therefore this is equals to positive 290.6 kilojoules per mole.